This video is brought to you by Hackeramo Chalk. Use code TPSA 10% off to get a discount.
Hello, welcome back. In this video, I would like to talk about special relativity, specifically the concept of a metric. So, as I said in the last video, I will expect the viewer to have some knowledge of special relativity. If you're looking for any resources to learn, I would highly recommend David Tong's notes on the subject, which I will link. They're quite good. Okay, so I'm going to start by discussing flat space or Euclidean space. So if I have 2 points, x1 and x2, then we know that the distance between them will just be given by Pythagoras' theorem. So I can call this delta s squared. Distance squared between them will just be like x1 minus x2 squared plus y2 minus, or y1 minus y2 squared, and so on, right? Squared 1 minus y2 squared. Right? This tells us how to find the distance between 2 points. If I want to find the infinitesimal distance between 2 points that are just infinitesimal, I can send this to a differential quantity. So this will become ds equals dx squared plus dy squared plus dz squared. Now, in a linear algebra way, I can write this as follows. I can define a vector, kind of dx is equal to just the components, dx, dy, dz. And then we can see that this is like an inner product. So we have dx, dy, dz, the vector. Then there's going to be some matrix. Because it takes this form, this is just a simple identity matrix. And then here's the rest of my vectors. So dx, dy, dz. Okay? Now, if this was a more complicated space, you can imagine that this distance might be some weird function, and then this matrix would become a lot different. Okay, and it is this matrix is what we refer to as the metric. So I can take this and I can write this in a different way. I can write this as a sum. If I change, okay, I'm going to change now from x, y, z and just label by x1, x2, x3 for the coordinates. I've made them upper, that's not powered, that's just notation for now. But when I do this, ds squared, the distance now becomes a sum over, so I'm going to say, use alpha and beta as my indexes from 1 to 3, and then we have some object which has indices alpha and beta, that's going to be our matrix, and then we have dx alpha and dx beta. Okay? So here, this you may recognize is the Kronecker delta. So it's just a set of numbers, and it can be defined as piecewise as 1, if alpha equals beta, 0 otherwise. Okay? So this is another way of writing this, where I just write, my matrix is just some symbols that has 2 indices, because it's like a matrix and has 2 of these. And that's one way of writing it. Now, there's this notation called Einstein notation, or Einstein convention, where we basically take this, and we know we're going to be doing lots of sums, so we end up just dropping this, right? We ignore the sum, and we say that the existence of an repeated indices implies that we are summing over these indices. So this is very handy, and will provide a lot of shorthand notation for what we do. You'll also see, like, if I have a matrix A times B, you may have seen this as a sum over an index like I. So this might be like J, I, B, I, K. So you sum over one of the intermediate indices. In Einstein convention, that's perfectly fine. We just drop this So this is still a matrix quantity because it still has two free indices, j and k, but the index I is being summed over. Okay, so that's kind of index notation. Now, the metric here in flat space is very, very simple, but we will find often that it will be quite complicated, even in flat space. So this is flat space, but another way of describing flat space is spherical coordinates. And if I plug in my equations like x equals or cos theta sine phi and y equals and I sub in all of those, I can get differential quantities, and I'll actually find that this same metric will become something like this. It'll become d or squared plus or squared d theta squared plus sine squared theta d phi squared. So it's a lot more complicated, and you'll see that the metric is no longer 1, 1, 1. It's actually like 1 or squared sine squared theta. So it can become a lot more complicated. Okay, so the distance between 2 points in flat spacetime, because there's a lot of symmetries in flat spacetime, should be invariant under certain things. If I do a rotation of both the points about some axis, then they should both still be the same distance apart because the space is flat everywhere. Or it shouldn't be, the distance shouldn't change depending on which way you look. So we can try see if that's reflected. In this metric, it's quite easily reflected. If I shift phi by some constant, well, then d phi is the same, and this whole metric stays the same. That's quite easy. But what about this coordinate, or these coordinates? So let's have a look at that. So let's say I have my vector x1, x2, x3. Then let's call these prime, because after a rotation, so I'm going to apply a rotation matrix. So I think this is cos theta, sine theta, minus sine theta, cos theta. So here I'm rotating around the z-axis, right? And then we're going to 0, 0, 0, 0, 1. And that's applied to our original x1, x2, x3. So that's a type of rotation matrix. And then we would like to see, well, is this metric preserved under this? We can check that. So we'll plug it in the linear algebra sense. Well, I can actually make these differential. That's also fine. Okay. So here we can see that this is the vector transpose. So if I go to write this down, I'm going to be writing x vector prime transposed times my metric, which I will call, which will be the same, and my vector x prime again. Okay, so now this is the, here, let me not have the differential. No, okay, no. Okay, so these are differential vectors. Okay, so let's plug this in. So dx prime, so this is dx prime. And let me take the transpose of all of this. So that's going to give me the regular vector down here, dx1, dx2, dx3. And then the transpose of this matrix. So cos theta, sine theta, so minus sine theta, because the mine will go up here. So the transpose, sine theta, cos theta. All right. Okay. Then I have my metric. This is a tedious exercise, but it will be worth it when we try to explain more complicated stuff later. Then we have dx prime, so we're just plugging in this thing. So cos theta, sine theta, minus sine theta, cos theta, 0, 0, 0, 0. And then my vector, dx1, dx2, dx3. Okay. Then all we have to do is some matrix multiplication. This is just an identity matrix times this. So this is just going to give me the same thing, right? Cos theta, sine theta, minus sine theta, cos theta, 0, 0, 0, 0, 1. And my vector. So I'm not going to draw for now. And then we just have to do this multiplication. So top row is going to give us cosine theta plus squared theta plus sine squared theta. The next one is going to give us sine cosine theta minus sine cosine theta. So cos theta sine theta minus sine theta cos theta. So it's just the same term, so they'll cancel. This component here is going to be the same. Cos times sine minus cos times sine. So that's also 0. And then this one here is going to be sine by sine squared plus cosine squared. So you may see what's happening here. All right. Cosine theta squared plus sine squared is giving me 1. The off diagonals are canceling. And so 1, 0, 0. Let me just bring it more in. Okay, a little messy, but there we go. So, and the 1's at the bottom, just give me 1 in the corner. So it just gives me back the identity matrix, and that's quite important. So remember I said that it should be invariant under rotations, and that's exactly what we found. We found that this metric is invariant under rotations, specifically because, sorry, I'll also refer to this. This is the line element, which I will often also be called the metric because it's related to this. So this matrix here, when we sandwiched it in between a rotation matrix, so we went OR transpose our metric, well, let me just call it G for now. And OR was invariant. This equaled our metric again. And that's actually a distinguishing factor of symmetry, how symmetries are relating to metrics. If a metric is only invariant under symmetry if this happens, because and it's or transpose explicitly because this is how it's set up in the linear algebra sense. We can turn this on our head. So here we had a metric, and then we used to have to check was the symmetry conserved, or did it preserve the metric? We can do that the other way. We can say, okay, if I want my metric to contain a symmetry, I can make it so that my metric must satisfy this. And that's what we'll see later. Okay, so now we're going to talk about some special relativity. So, or I might often refer to it as SOR. Special relativity is one of what I mentioned in the last lectures of the principal theories. So it's based on some principles or postulates, and things are derived from there. So the two in special relativity are, the first one is the constancy of the speed of light. Let's see, so if I call the speed of light speed, it's in all frames, all inertial frames. And the equivalence of physics in inertial frames. What I mean by that are like equations of motion should be the same in all the inertial frames. So Okay, so as I said, you should be familiar a little bit with special relativity. So you should be familiar with what I will call boosts. So if I'm in some coordinate frame S, then I can change to some coordinate frame S prime, which is moving with some velocity with respect to my original coordinate system. So then you know that from these postulates it can be derived that my coordinates, my x, y, z, and my time will change a bit. So specifically that's what's different between special rel and Newtonian or Galilean kind of understanding of inertial or change of coordinates. So we'll get something like this. You'll get some factor gamma, and then you'll get t, and then it's minus xv over c squared. So v is the velocity of the change. So this one is just x minus v t, and these ones stay the same. So in this one, I'm just boosting along the x-axis. It doesn't matter really what way I boost in. I can always just change my coordinates until that is my x-axis. So everything we do with this simplified version should be equivalent. Okay, so this factor gamma, you may remember, is 1 over square root of 1 minus v squared over c squared. All right. Okay, so what we want to do with this is we want to write it in a more similar way to what we were doing earlier. So I can actually extend my vector I had earlier, which had 3 components, and make what I'm going to call a 4 vector. So in order to do this properly, I need to, the first component, I'm going to make ct instead of just t, just so that this has units of distance. Okay, then I have, as usual, my x, my y, and my z, and that's a 4 vector. And then I can now write this Lorentz transformation, put primes in this, as a matrix. So we can read off what it's going to be. So this first component is going to be gamma. This second one is going to be minus gamma v over c. Same for down here. Minus gamma v over c. This one's also going to be gamma, and then the rest are 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. All right, and that's times my ct, x, y, z. Okay, so this is kind of my transformation. Before I had a matrix 4 that did a rotation. Here now I have my matrix that performs a boost. So this is called a boost matrix. Now, I'd like to write this in a similar way to how I wrote the rotation matrix so that this becomes more similar. So first, I'd like to notice one thing. If I try to calculate the determinant of this matrix, all right, because these are just ones, it just depends on the determinant of this upper 2 by 2 matrix. So this is going to be, so gamma times gamma is gamma squared, then minus gamma v over c times gamma v over c. So that's going to be gamma squared v squared over c squared. So I can just factor out the gamma, and that's 1 minus v squared over c squared. But remember, this is gamma is 1 over square root of 1 minus v squared. So this is just equal to 1 minus v squared over c squared all over 1 minus v squared over c squared. So here I'm talking about determinant of, I'm just going to call it lambda. And that's just equal to 1. So the determinant matrix is equal to 1. And that's true if I boost in any direction. Okay, so if the determinant of this matrix is 1, and these upper 4 components are what I care about, and this is the same, these 2 components are the same, these 2 are the same, well then I can write it something like this. So A, B, 0, 0, B, A, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Okay. Now the determinant of this is just a squared minus b squared equals 1, as we showed over there. Now, you might, whenever we see an equation like this, we're very tempted to parameterize it by the hyperbolic equations. So I can let A equal cosh of some parameter we're going to call psi, and B equals sinh of that. I'm doing this because now cosh and sinh are going to look very similar to my cos and my sine I had of the angle theta earlier. Okay, so let me write this in. So we said A, which is our gamma, is cosh psi. This is sinh. This is also sinh. And this is cosh. Okay, now, what we would like to do is we know that space and time through special relativity are very intimately linked. So what we want to do is we want to find a metric like the one we found earlier, but for space and time. So how are we going to impose this metric? Well, we're going to say that it must be invariant under Lorentz transformations. So under boost, so we know that flat space is invariant under rotations, but now I want extending this to, I want it to also be invariant under boosts. So I'm going to impose that and then try to find my metric based off that. Okay, so to do this in a short way, we're going to kind of make some guesses. So hold on, let me rub all this out. Okay. So let's make the guess that it's going to be the same. Let's just say, so it was an identity matrix, right? The last time our metric. Remember now that the condition, so this is our boost matrix, and the condition we arrived upon was that this transpose times our matrix times it again should be the same, right? That's because we're taking the inner product. This part comes from the transpose of the transform vector x prime transpose, and then so there should be x there and x there. So that's your x prime transpose, and this is just your x prime. So this is for x prime is transformed by this matrix lambda. Okay, but all we care about is this middle bit. All we care about is this. So let's try to do that. So we have cosh psi sinh psi 0 0 sinh. So transpose, there's no sign change this time because they're both the same. 0 0. And we got 0 0 0 1 0. We should space these out a little better. 1 0 0 0 1. Okay, that's the transpose. And then we have our metrics. So we're going to make the guess 1 0 0 0 1 0 0 0 0 1 0 0 0 0 1. Right? So I'm guessing the same form, right? We already have a pretty good idea that if I fix my time, I'm going to get back just the spatial one, so that this should probably be the same form. The only question is, what does this extension on t look like? So then we get just this part, which is just the matrix. So cosh psi, sinh psi 0 0, sinh psi, cosh psi 0 0 0 0 0 1 0 0 0 0 1. You can begin to see why we use index notation, so that we don't have to write out all of these. Okay, so identity matrix times this, just going to give me the same thing, right? So then the question is, what is the identity matrix times, or no, what is this times itself, basically. Gosh, psi 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Okay, so this is going to give me, okay, cos squared plus sine squared, so cos squared psi plus sine sinh squared psi. Second row is going to give me sinh by sinh, and no, sorry, this is, sorry, no, yeah, sorry, cos by sinh plus cos times sinh, so this is 2 sinh psi cos psi. The next ones are just 0 and 0. This one's going to give me the same as that one, so 2 cos psi sinh psi. This one's going to give me the same as the diagonal, so again cos squared plus sinh squared psi, and the rest are zeros, so ones on the diagonal. 0, 0, 0, 1. Okay, now what are we trying to find? We're trying to find a metric such that we put it in the middle of these, we get back that same metric. Where we're running into a problem here though. The cos plus sinh is not going to reduce to 1. Remember, the identity is cos squared psi minus sinh squared psi is equal to 1. There's a minus there that we're not getting there. So how do we fix that? Obviously, our guess of just the flat metric, again, extended, didn't work, but we can fix this. We cleverly note, let me write it out again. Sin psi, cos psi. Okay, what if instead of 1, 1, 1, so this is going to be 1, 1, 1, I made it with a minus in the first component. Alright, now the rest of the matrix is still going to be an identity. The spatial bits will all have our 1, 1, 1. And then this is the same matrix again. I'm not going to write it out, the lambda. Okay, now what does this change? So basically it's this matrix multiplying it again. Well, if I multiply, first row will give me up a minus, and then same again for the it's just this first row that are going to get this minus. The first row comes up and gets, sorry, top components. Hold on, I'm writing it. So this is sinh. Okay, so when my first row comes up, this cos and this top component is going to get a minus, and this sign here, sinh here, is also going to get a minus. So basically, this just amounts to, and the rest of them, because they don't interact with this top minus, they only interact with the 1, 1, 1 of the diagonal identity. They stay the same. So I now have minus here, and then left with that times this last matrix. So now I have minus cos by cos, so that I'm going to change that to minus cos squared. The second bit is sinh times sinh, so that's still plus sinh squared. Then the other component, so it's going to be the second one here, minus cos by sinh is minus cos sinh plus plus sinh by cos. So that is now going to cancel instead of giving me 2 here. 0, this is going to be 0, and then this one down the bottom, this one's going to be minus sinh by sinh, so minus sinh squared and plus cos squared. So now these give me what I want. If I multiply, so this is cos minus sin squared, so minus cos plus sin squared is like I multiplied this by minus 1 on both sides. So that gives me a minus 1, and this one gives me a 1. And that's exactly the metric we guessed. A minus 1 at the top and then 1, 1, 1 down the bottom. So we can see that this metric, where we have the exact same for space, but we change sign for the time one, will give us what I want. Okay, what does that look like? Let's just, last thing we do, write down the line element. So ds squared, we can now think of putting our minus 1, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. And if we had our t, x, y, and z sandwiched in there, right? We can see that the t will pick up a minus, but none of the others will. So infinitesimally, we're going to get a minus, sorry, I missed my c's, my ct's. We're going to minus c squared dt squared, and then plus the same rest of the metric, dx squared plus dy squared plus dz squared. Now this is a metric for special relativity. If we want to calculate, so this is what is invariant. So before we had that lengths are invariant in Euclidean space, this is what is invariant in the metric that includes boosts. Okay, so this metric will be our base for when we go to more complicated metrics that obviously will have to include some curved spaces. Okay, so at the start of this lecture, we began by starting with the fundamental length in Euclidean space as being invariant under rotations, and then that led us that led to the metric, and then we checked that that was invariant under rotations. We want to go backwards now. We have a metric, and we want to know what is the fundamental quantity for that is invariant. So we need to be cognizant that we don't have just space anymore, we have time. So we don't just have points in space, we have points in space-time, which are going to call events, okay, because they take place at a certain point in space and at a certain time. So we call them events. So I'm going to do another notation, simplification, and just go call, so ct x0, x is x1, y is x2, and so on. So I just have x0, x1, x2, x3. Okay, so we got the length in Euclidean space by taking it as like an inner product with our metric. So we now want to know, well, what happens if we do that with this one? So we have, this is our vector. So the inner product can look something like this. x0, x1, x2, so this is a transpose vector. Then we have our metric, which we established was 1, our minus 1 in the top, and then an identity matrix. Right? And then to get an inner product, we're going to have the same again. x0, x1, x2, x2. Okay? So now let's do this when we do this inner product. We're going to see we're going to get kind of the same form, but we're going to get a minus x0 squared and then plus x1 squared plus x2 squared. Okay, so it is this strange quantity, which if we fix time, goes back to distance, but now it's a little strange because of this minus sign. So this quantity is invariant under our Lorentz transformations and under our rotations as well, because they are part of this, because they leave this lower block unchanged. Okay, so I want to try to figure out what this quantity is. How do we physically interpret it? So here I'm going to try rely on, hopefully, your knowledge of special relativity to just makes it easier than doing it all out mathematically. Okay, so in special relativity, we often draw Minkowski diagrams. So I'll have like CT on this axis, X on this, right? And then a boost, what a boost does is it changes the axis. It kind of moves them in. So CT prime gets squished in like that, and X prime gets squished in like this. Okay? So then I can ask, okay, let's say I have 2 points. For simplicity, I'm going to make one of them the origin, which is nice and easy. And I'm going to make another one, let's say, out here, right? Then I can ask, so here's X, here's point X prime. Then I can ask myself, what is the invariant quantity, which is the difference, which squared is the, so the difference between them squared, which will give us like that same form with a minus for the time component and a plus 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 for the rest of them. So what is that quantity? Now, the important thing about this quantity is it is invariant under Lorentz transformations. So I'm going to abuse this now. I'm going to make a Lorentz transformation such that this this timeline. So remember I said time when under Lorentz transformation squishes them in. I can make a Lorentz transformation so that this point in space-time is directly ahead of me in time. So that's like I'm on a ship and I go to a velocity such that the space-time point is directly ahead of me. So now in this frame, so let's just simplify. Let's forget about y and z for a minute. Let's just deal with the one-dimensional case, as everything can be changed such that it's one-dimensional in this sense. So I just have t and x, but now I see that x prime is 0 because I'm on this t prime axis, right? So that means that my invariant quantity, delta s squared, is only x naught prime minus the other point, which is just x naught, but squared. And it gets a minus out front because that's what the metric gave us for the time component. This one is just 0, so this, because it's at the origin. Okay, so minus x naught squared. So x naught now, or x naught prime. X naught prime will be, so this is the time, so this is the time component in the new frame. So this is essentially the time taken to get from here to here. So I can interpret this quantity as the square minus the square of that time. So if we ignore the minus, the magnitude of this quantity squared is the same as the time to get from here to here. That's what we call the proper time. It's the proper time to get from a point to any point in, from this point to this new point that I've looked at. So we will often call so for any vector x, it's the square will be given by tau, as that's what is often used to denote the time to get from here to here, in the frame of the observer who goes straight from there to there without, because they're not moving in that frame. Okay, so that was in this very special case where this space-time point was in what's called my future light cone, right? If I draw a 45-degree line, we know that these are the path that light rays take. If this point was out here, I can't boost until that point. I can only squeeze this up to maximum 45 degrees if I go to the speed of light. I can't make it any further. But what I can do is if I squeeze enough, we see that the x prime axis, here's CT prime has been visually, the x prime axis will reach that point. So now the what's going to go on here? Now, along the x prime axis, you have an observer going at this speed will experience everything along this axis to be at the same time. So this point now is not further in time than you, then so these points are not separated by time, they're just separated by space. Space-like separated. And for this observer traveling really fast, they just see this as a distance. So then this one will become like x prime, x1 prime is x1. And then this is 0 because that's the order. So it's just x prime squared. So it's just a distance. So this quantity is sometimes a distance and it's sometimes a time, right? Which may be a little weird. But it is what we call the proper time. And so proper time is usually the generic term. Refer to it because usually the points in the future light shown that we're interested in. But if it's space-like separated, then it's also it's going to become a proper distance.